an independent editorial defense analysis focused on Australia's strategic environment.
The impending closure of the Boeing F/A-18 Super Hornet production line in St. Louis in 2027 marks a definitive transition point for the Royal Australian Air Force. This industrial reality moves the fleet management strategy away from active acquisition. Instead, it shifts toward a complex phase of sustainment and capability optimization. This necessitates a fundamental reevaluation of the Super Hornet within the broader Australian defense architecture. Rather than viewing the platform merely as a strike fighter reaching the twilight of its service life, defense planners are increasingly treating the 24 F/A-18F airframes differently. They are being positioned as critical command nodes, central hubs within a distributed manned-unmanned teaming system. This shift represents a pragmatic adaptation to the constraints of a medium-sized air force operating in an anti-access area denial environment. An environment where pure mass is unavailable and technological asymmetry becomes the primary lever of operational relevance. From a systems perspective, the decision to retain the Super Hornet fleet through to 2035 implies a specific operational logic. It is a logic that prioritizes payload capacity. It values command and control functions over stealth or survivability in contested airspace. The strategic rationale rests on the integration of the locally developed MQ-28 Ghostbat. This program acts as a force multiplier that fundamentally alters the value proposition of the aging Super Hornet airframe. In this configuration, the F/A-18F ceases to be the primary sensor. It is no longer the tip of the spear. Instead, it functions as a localized tactical battle manager. It coordinates a formation of autonomous systems that penetrate hostile air defense bubbles. This architecture allows the Royal Australian Air Force to project force into high-risk zones without exposing manned platforms to unacceptable attrition. Effectively, it decouples the lethality of the package from the survivability of the launch platform. The technical divergence between the Australian sustainment strategy and that of the United States Navy highlights a distinct approach to capability risk management. While the United States Navy has pursued extensive structural life extension programs, physically reinforcing airframes for carrier operations, the Australian approach is different. It focuses heavily on software configuration. It prioritizes avionics throughput. The priority is to ensure the Block 3 software capability is compatible with the advanced data link requirements of the Ghostbat. This decision reflects an understanding that in a modern conflict scenario in the Indo-Pacific, the kinematic performance of a fourth-generation fighter is less critical than its ability to process and distribute targeting data. However, this creates a dependency on a distinct supply chain for avionics and software integration, one that may diverge from the primary American logistical pipeline over the next decade. A critical, often underappreciated variable in this equation is the human factor, specifically the two-seat configuration of the F/A-18F. The role of the weapon systems officer becomes paramount, and in a manned-unmanned teaming construct, the cognitive load required to manage a flight of 3 to 4 semi-autonomous drones while simultaneously navigating a hostile electronic warfare environment is substantial. Current operational assessments suggest that this workload may exceed the capacity of a single pilot in an F-35A. Consequently, the back seat of the Super Hornet offers a tangible operational advantage. It allows the weapon systems officer to function as a mission commander for the unmanned elements. They monitor autonomy levels, they authorize kinetic engagements, and they manage the electronic signature of the formation. This division of labor suggests that the Super Hornet provides a capability niche that the more advanced but single-seat the F-35 cannot currently replicate without significant advances in artificial intelligence. The integration of the MQ-28 Ghostbat also addresses economic constraints. The cost per flight hour of the Super Hornet is projected to rise as the fleet ages. By utilizing the Ghostbat as a reusable but attritable asset, defense planners can theoretically generate a greater mass of combat power for the same investment. This approach aligns with the intent to build sovereign industrial capability. As the Ghostbat is designed and manufactured within Australia, it reduces reliance on foreign military sales queues for replacement hardware. It introduces a layered force structure. Expensive, irreplaceable manned platforms are kept at a standoff distance. They launch long-range effectors like the AGM-158C long-range anti-ship missile. Meanwhile, its cheaper unmanned assets conduct the dangerous work of target identification and decoy operations. However, this transition is not without significant systemic risks. It involves trade-offs. The reliance on the Super Hornet as a network node assumes a robust data link architecture, one capable of withstanding intense jamming and cyber interference. If the tether between the manned controller and the unmanned wingmen is severed, the operational utility of the entire package degrades rapidly. Furthermore, the logistical challenge of maintaining a legacy fleet until 2035 cannot be overstated. As the global user base for the Super Hornet shrinks, the economies of scale that currently support the supply chain will erode. This will likely lead to increased unit cost for spare parts and longer lead times for maintenance. This places a premium on the ability of Australian industry to manufacture or refurbish critical components domestically, a capability that is currently still maturing. There is also a doctrinal tension regarding range. While the Super Hornet is a capable platform, its combat radius is inferior to the strategic geography of the northern approaches without significant aerial refueling support. The Ghostbat creates an extension of sensor range, but the kinetic reach of the system is still tethered to the fuel fraction of the manned host and the availability of the KC-30A tanker fleet. This physical limitation dictates that the Super Hornet and Ghostbat team is best suited for defensive counter-air and maritime strike roles within the near region, and it is less suited for deep penetration missions which would require the stealth characteristics of the F-35 or future platforms. The decision to extend the Super Hornet, therefore, is an implicit acceptance of these range limitations. It is an exchange for the capacity to field a greater volume of fire and sensors. From an industrial standpoint, the relationship between Boeing Defence Australia and the Royal Australian Air Force becomes the center of gravity. The success of the program depends less on the raw aerodynamic performance of the aircraft and more on the agile development of mission software. The ability to rapidly update the algorithms governing the Ghostbat and its interface with the Super Hornet in response to evolving threat libraries will be the true measure of system effectiveness. Ultimately, the trajectory of the Australian A-18F fleet suggests a calculated bridge strategy. It is not a permanent solution to the evolving threat environment of the 2030s. Rather, it is a mechanism to mature the manned-unmanned teaming concept while awaiting the arrival of next-generation air dominance systems. By leveraging the existing capital investment in the Super Hornet and pairing it with a nascent sovereign unmanned capability, Australia is attempting to bypass the linear cost curve of traditional air combat power. The effectiveness of this strategy will depend on the successful management of technical integration risks It represents a shift from measuring air power by the number of hulls on the ramp to measuring it by the resilience and lethality of the integrated network they support.